Okay, so today we're going to talk about two problems, 2SAT and max 2SAT. So this will build very closely on what we did last time. So yeah, last time was a bit of a trip. So compared to kind of doing these more conventional algorithm lectures where we just have a clear problem, we're trying to solve it. We focused on the satisfiability problem. There was no graphs, it was just Boolean logic. We're kind of exploring this. The basic question is, if I give you a Boolean formula, can you find a satisfying assignment? Okay. And what may or may not be surprising to you, I think I first found it surprising, is that we don't have particularly great algorithms for this problem. But maybe one perspective in hindsight is that Boolean algebra is fairly expressive. And insofar as expressive as it is, that makes it harder and harder to believe that you can solve any of them. Right? So yeah, big question, is there a polynomial time algorithm for Boolean satisfiability? We still don't know. Right? And then if you polled experts, I feel like most people would say there probably won't be, but I think there's still like plenty of holdouts on the yes side that are quite credible. So we'll see. Plus there's, however much venture capital, which is roughly being poured into claiming you can solve all questions. But given that we couldn't come up with an algorithm for Boolean stat, we started looking at special cases like CNF stat, where it's just like an and of ors, so which would kind of look like a flat tree. And what we showed, which is maybe more interesting or more rich, is that even though CNF stat might seem nicer, it's not that much nicer in the following sense. If you had a polynomial time algorithm that can solve CNF stat, so stat in this particularly nice, convenient form, you would be able to solve any Boolean formula in polynomial time. Okay? So we didn't come up with an algorithm, which would be the most satisfying thing, but we were able to say something quite precise about the problem anyway. Yeah, we're still able to walk away and come up with a much better understanding of CNF stat than we did going in. And yeah, just to kind of diagram, the style of proof. So, normally we try to fill in this box and get an algorithm for CNF stat, but given that we struggled to think of anything, there's a lot of ideas that come to mind. Can you do this? Can you do that? I was playing back the tape and there's all sorts of ideas. But if you want to show that it's hard, or you want to argue that it's unlikely, right? What you can do is you can presuppose, what if I did have an algorithm for this? And what we did was, okay, I can take my general Boolean formula. And if you remember the the technical technique was sort of to use assignment to break up all the little subtrees. So you kind of get this big flattened CNF stat formula. But one way or another, you can take your big, deep, complex looking tree, put it in this normalized form without dramatically increasing the size of the formula. That's important. If we had just done the standard, what's the person's name? The Morgan's Law thing, it would blow up exponentially in size. But substitution, this assignment trick, I think the key trick is that you're allowed to insert variables, which might not be obvious if you're coming from a purely mathematical background. But once you're allowed to insert variables, because you actually realize what you're really working with, this slightly broader context, then we just have this trick. We make this formula and say, oh, this box would have been able to solve this problem, which maybe I'm more willing to believe is very hard. Okay? And so at the end, we have something rigorous where we show the CNF stat, we at least have some rigorous reason to believe that maybe we won't get an algorithm for it, which is, it's better than nothing, right? Ideally, we just get an algorithm for it and then get all the Bitcoins or something, but this is still also interesting. I kind of rushed this, but you can also do something like 3SAT, where there's exactly 3 variables. Maybe in PSO, you guys looked at KSAT and K+1 SAT and things like this. So you can look at more and more structured versions of SAT and ask yourself, oh, is this finally easier, or does this turn out to be just as hard? I think K and K+1, they actually both turn out to be just as hard for larger Ks. You can also do it for circuits, which would just be yet another generalization of Boolean SAT. And I didn't really go through this slowly, but just like we're able to pull apart a tree one subtree at a time with the assignment trick, I could just take all the internal nodes kind of working bottom up in a circuit and gradually replace things with assignment tricks and get another flattened CNF. So same idea, nothing special. But now I think you at least get the pattern. So, right, so we walked away with a different style of conclusion than we've kind of had up to this point in the class. We didn't get any new algorithms. Instead, we started, but we're still able to kind of understand relationships between problems and sort of understand relationships between the structure of various problems. So we still have that level of rigor, even if the solution is taking a different, or the outcome conclusion is taking a slightly different form. Okay? And this is sort of the broader context in which algorithms actually appear. You're given a problem, you want to solve it. If you solve it, great. But if you don't solve it after 1 month, and then you give it to ChatGPT, it doesn't solve it either, then you might start wondering, oh, can I reason that it should be hard or something like this, right? If you can come up with a conclusion like this for your problem that it's too good to be true for a strong reason, that's also a nice, satisfying, rigorous thing. Then maybe that tells you, oh, I should change the problem or something like this, right? So we can still be constructive even when we can't be as directly constructive as coming up with an algorithm. Okay. All right. So yeah, today's going to be kind of fun because it's really going to bring this sort of connection into focus. So we're going to look at even simpler SAT problems, okay, with exactly 2 variables per clause. So we did 3 SAT last time. That was exactly 3. This is just exactly 2. Nothing mysterious. And the same problem as always, can we get a polynomial time algorithm for 2 SAT? And in addition to 2 SAT, we're going to look at a slight variation of 2 SAT called max 2 SAT. Okay? So max 2 SAT, same input. I give you a 2 SAT kind of formula. It's in CNF. There's 2 variables in every clause. And your goal is not necessarily decide if it can be completely satisfied or not. You know, if you think of like each of the individual clauses, these individual ors, because it's an and of ors, think of those as like points. You want to get as many points as possible. You want to satisfy as many clauses as possible, whether or not you can actually satisfy all of them. Okay, obviously very similar problem, but one is just a yes, no, can you satisfy all of them? The other one is more of a quantitative, what's the maximum number you can satisfy? Okay. Of course, I can take the max problem and turn it into a yes, no problem by asking like, can I satisfy at least k clauses for some variable k? Right? Once you can do that, you can binary search for k or whatever. So you could put into yes, no form, but the key point is, we're focusing on maximum number of a formula that might not be completely satisfiable. Okay? And I think we all agreed these look like awfully similar problems. Okay, so this time I've set up the poll ahead of time. So we're going to look at each of these 2 problems and try to figure out if they're hard in the sense that getting a polynomial time algorithm would say solve Boolean SAT or something else we think is hard. Or we'll actually come up with an algorithm just like we have been in past weeks. Okay? So as usual, so we have four things, and we'll do 2 SAT first and then max 2 SAT afterwards. But as usual, you can just not vote. So who's not voting? All right, down to 1. Okay, so for 2 SAT, you can either vote that we think we'll come up with an algorithm by the end of class, or vote that we're going to show that it's hard like the other other problems last week by the end of class. So who thinks we'll get an algorithm? Oh, fair number. I'd say like, okay, and then who thinks it'll turn out to be hard? Okay. Okay, so that's, okay, so close to half and half, but slightly more in favor of getting an algorithm. Now max 2 SAT. Again, just like 2 SAT, but you're just trying to do as much as possible instead of figuring out if they're all satisfiable. So for max 2 SAT, who thinks we'll get an algorithm? A bit less this time. I'll put that like 22%. And then who thinks it's going to turn out to be hard? A bit more this time. Okay. Put that like 76%. Okay. Good. Good. Okay, so maybe I should first ask. Okay, let's take 2 SAT first. Does anyone want to suggest why you either thought they would be hard or why there might be an algorithm? Or maybe it was just a coin toss in your head because it came out somewhat close to 50-50. That's also a valid answer. 57%, I guess, voted algorithms. Did you have any hunch for an algorithm? Or, yeah.
You have one like x1 on and one x1 off, then you can get rid of x1 and like get the other two or game.
If you have one X1,
If all you have for one of the variables, this is not a full algorithm, but like it's why it feels not that bad. Like you know that it has to be either on or off. You have one where it's that and one where it's the like opposite of it.
yeah.
In the OR gate, then you can get rid of x1 entirely and like connect the two together that are on the other side of those ports into one more.
Oh, okay. But somehow it feels like maybe you can make some progress somehow. So you're imagining like, oh, X1 appears in this clause, X1 bar appears in another clause, and somehow if I pick one, then the other two must have certain constraints. Okay. Although I'm already a little bit worried about things blowing up when X1 appears a bunch of times, X1 bar appears, but okay. But somehow your mind was thinking of some ways to process it, and you thought, okay, maybe if I buckle down, I can get an algorithm out of this. Okay. What about anyone on the hard side? I sometimes get just like, well, he's going to mess with us. It's probably going to turn out to be hard. No opinions on the hard side? Yeah. It'll probably be, you just had this hunch, like, why are we here if it wasn't hard? Okay. That's fair enough. All right. Max 2 sat. More people voted that it was going to be hard than polynomial time this time. Easy. Did anyone go? Somebody must have gone from poly time to hard. Anyone want to explain why? Like they were more pessimistic for max 2 sat than 2 sat? Yeah.
The end outcomes.
2 to the n outcomes?
Like there's lots of ways that you can have it on and off.
Yeah.
But like probably inject all of those results.
Well, why are there 2 to the n outcomes? Oh, well, you're just trying to maximize the quantity. So, well, what's 2 to the n is how many inputs assignments.
We're getting somewhere in the middle. Like we have like 5 of them on and 5 of them off. There are like a lot of different ways to accommodate those. And if we're trying to prove that it's like either the most or the least, I feel like we're gonna have to go through some of the other steps.
True, but could something similar be said of 2 sat?
Well, then it leads to how to get the balls off. So like,
Oh, okay. So you're saying that maybe the max, something about the max is introducing a degree of freedom? Okay. Any other ideas? Yeah.
Max 2sat is at least as hard as 2sat because a polynomial time max 2sat algorithm, if you calculate max 2sat for any given like equation with 2sat Holden equation, and you get this, you can use that result to determine what your answer for 2sat is. So like you can't do it necessarily the other way around. If you know the answer to a 2sat for specific, if you're an algorithm that gives you 2sat polynomial time, that doesn't necessarily mean if you return false, you can still like decide how many you can at maximum satisfy. It goes one way but not the other.
Yeah, exactly. So if I could solve max 2 sat, if I had a black box, I could maximize the number of clauses I wanted to satisfy, or that I could satisfy. And I wanted to solve 2 sat. I just want to know if they can all be satisfied. I can just give it to that black box and see if it can satisfy all of them, right? If it can do all, it will max it out. On the flip side, if you're trying to solve max 2 sat, you have a black box for 2 sat, you can give your formula and it'll just be like, no, can't satisfy all of them. And you're like, okay, well, now what? Like, it doesn't tell you anything about the max. So one problem is actually strictly harder, or at least as hard as the other, insofar as one reduction is very obvious. Okay, so at least we got like that directionally correct in our vote. Last year we got it directionally backwards, and I think they were embarrassed. But okay, so at least we can sort of see that max 2 sat shouldn't be easier, is at least as hard as 2 sat insofar as it can solve this exact 2 sat version. And it's a good sanity check. All right, so let's see what comes up next. Okay. So we are in fact going to try to come up with an algorithm for 2 sat. So 57%, congratulations. And I guess I have this slide here to let people guess and suggest any ideas. So I put up two examples of a two-sat formula. You've already seen the top one. So the top one, if we remember from last class, is not satisfiable because I enumerated all the pairs. So no matter what you do, one of those pairs are going to cause some problems. And the third one, I guess, is satisfiable because it's omitting one of them. It's not very interesting examples. But in any case, any ideas for trying to develop an algorithm? Because obviously I'll eventually show the algorithm. It's more fun to guess before you know the answer. Yeah.
Well, since there's only two variables in each of the clauses, you can kind of force the values a little bit because, like, if you start by supposing like x1 is false, then you look at that first clause, and in order for that overall clause to be true, then x2 has to be true. And so you can kind of like go down and change that.
Okay, so there might be some forcing, at least this observation maybe is intuitive. Let's take this first clause here, right? I know I have to take x1 or x2. And if I set x1 to be false, then I would know that x2 has to be true just to satisfy that first clause. Vice versa, if I had set x2 to be false, that would force something on the x1 side. That's not true for 3-sat, right? If you make one decision, there's still 2 degrees of freedom left. So it's, kind of the combinatorial branching is higher, I guess. I'm just making up words. But here it feels like, is it limited enough that we can really force something kind of all the way through, like force moves? Yeah.
I think you can take x1 and then link everything that's on the right side of those x1 not fit to everything that's on the right side of x1 clicked. And exactly one of those is true, so all the words have a full.
Okay, so you might be anticipating what's coming up. Let me just go through it slowly. So I don't know, I guess we just did this. But if you take a clause like this, right? Maybe just to make sure we're all on the same page, I didn't go too fast, okay? So take that, I guess that first row. If I said x1 to be true, what would that force x2 to be? True? Yeah, it shouldn't be too hard, just read them out. Okay. And then for that second clause, if I set x1 to be true, that would force x2 to be false. So at least for our top formula, that tells you can't set x1 to be true because it forces x2 to be both, right? This is more figuring out the solution can't be satisfied, whereas you're more focused on satisfying maybe, but okay, now vice versa. I could say, what if x1 was false, right? That's my only other choice. And that would force, in the first row, this clause would force x2 to be true. Yeah, you need to set it to be true to make that clause happy. And in the second one, well, okay, it's a pattern. But, if you had tried to set x1 to be false, you would find this contradiction, right? One of the clauses forces x2 to be true. The other clause forces x2 to be false. By now, we've exhausted all the options for x1, and we conclude, okay. So what's also kind of interesting is, we also have somewhat of a certificate that you can't do this or that. Okay. So I think this was already sort of suggested implicitly in our brainstorming. Could use the word link. So I'm going to interpret that as something graphical. So maybe we can start trying to model this sort of forcing, this something implies another kind of interaction with a graph. And that's what we'll do. But if I were going to do that, does anyone want to suggest what could be a candidate? What would the vertices be? What would the edges be? Or map to conceptually, yeah.
Probably not like each value be a vertex, and each also not value.
Okay, so by value you mean like x1 or x1 bar? Okay. So I think the wording we use is literal, but anyway. So each xi and xi bar. So in other words, that ith variable will generate 2 vertices, one representing xi, one representing xi bar. That's what you had in mind, right? Okay. Now, those are reasonable candidates for vertices. So now we have 2 n vertices if there's n variables. What would an edge look like? Yeah.
It's when
Great. So for each clause, so when I say A or B, A could be xi or not xi, and you just have to flip the signs accordingly. So let's take A or B, right? If I don't set A to be true, and I set A to be false, then I have to set B to be true. Okay? So I'm going to write not A to B, meaning if I set not A to be true, which is the same as setting A to be false, then I would also have to set B to be true. Okay, so it's like true here implies true there kind of relationship. And then it's symmetric. So A or B, if I set not B to be true, which again is the same as saying B is false, it's always confusing, then that forces you to set A to be true. Okay, so we have these two forcing relations, and it's really saying if the source is true, then the destination has to be true. Okay, and A could be xi, A could be xi bar, so you just flip things accordingly. Yeah, so that's sort of, I think, encoding this forcing idea, but we're now modeling it as a graph. Okay, so let's study this graph. Or here's an example of a graph. So here I've drawn out what the graph would be for that formula we know is wrong or is not satisfiable. So I think, and I've also annotated the edges. So something like x1 bar or x2, I have an edge going from x2 bar to x1 bar, because if I set x2 bar to be true, which is saying that I set x2 to be false, then I would have to take x1 bar. So I would have to set x1 bar to be true. Okay, so I have this edge there. And I think this same clause is also going to appear up here in the top edge. If I set x1 to be true, so x1 bar is false, then I know I have to take x2, so there's an arrow to x2. Okay, so it's a little, maybe it's slightly confusing just because we negate the variable on the source side. So you just have to get used to that. But otherwise, if you go slowly enough, it's straightforward. Okay. Yeah.
Maybe just for like visualization.
Yeah.
What would the graph look like if it was just rapid clause?
I'm glad you asked. I hope I'm glad you asked. Oh. Yeah, here's one down here. So, and I'll put them side by side in a moment. But yeah, this is just removing, I guess, the last clause, which was apparently x1 or not x2 seems to be the missing one. And there's slightly fewer edges. Okay, 2 less edges from 1 less clause. And I'll put them side by side in a moment. I'll ask you to try to guess the difference so we can build an algorithm. Let me start a little more slowly though. So just to kind of parse out the graph and get a sense for it. Okay, so consider an actual assignment of true-false values to the variables, right? Of course, it's satisfying if all the clauses come out to be satisfied, but at some level, like, how can I read that off in the graph? You know, if I plugged in true, false, and stuff like this, what should I see or not see in the graph that's sort of equivalent to satisfying all the clauses? Yeah.
If you start out one node, and you sort of like and you sort of like explored all the edges going out from it, and sort of like do it like there shouldn't be a walk that goes from that node to like the node representing the inverse. So like it implies something that will eventually imply not x1.
Yes, that's actually absolutely true. You're one step ahead of me. But for the moment, okay, I'll just show the box. So the first thing I just want to point out is that if you have if I just plugged in the values into this graph, and I wanted to just look at the graph, maybe I'll hide all the labels on the edges, right? Imagine I erased all these annotations that's just true, false, or something. And I want to say, oh, is my assignment satisfying? You know, based on our edges, whenever we have true, it must go to a true, right? And so if you had true going to false, then you have some error. And if you don't have any true going to a false, then you're okay. You'll satisfy all the clauses. That's the only thing I wanted to point out in terms of interpreting and understanding the graph. So now let's get to the, I think, deeper point that was being suggested. So, all right, so you're talking about trying to surface contradictions in the graphs. Let's try to articulate that. So I put side by side sort of the auxiliary graph for the formula we know can't be satisfied, and the one that can be satisfied. And one of your suggestions was like, well, x1 shouldn't be able to reach x1 bar because then if I set true here, I wouldn't be able to set true here, and I have some issue, right? But it's a little stronger than just that because I could have just put false here, and then there would be no problem, right? So it is possible that x1 can reach x1 bar. That's not necessarily an issue. Up here, let's see, is there a good example? Yeah, up here, x1 can reach x1 bar, right? But this formula is satisfiable. So that's not quite the condition, or that can't quite be the condition. So we're looking for some kind of patterns in this graph that help, looking at the graph, try to figure out the formulas are wrong. Yeah.
There's a cycle in the last one where that includes x1 and x1, but not the right one.
Exact. So pushing that logic further, a cycle would be really problematic, right? Because, either x1 or x1 bar has to be true. And if you have a cycle like, if you start here, you'll get to here, that would be an issue if x1 was true. Or if x1 bar was true, the other half of the cycle going from here to here will give you some issues, right? Because you can't have true to false in a satisfying assignment. So if you find a cycle in this graph, then you definitely found some issue. So yeah, the one difference in this graph is that here I have a directed cycle that contains, both literals for one variable, x1 and x1 bar, which is the graph telling you, oh, there's a contradiction. And over here, there is no directed cycle with complementary literals if you look carefully. Okay, I don't think you'll find one. So you go this way, and then I guess you're stuck. Or you can go this way, and then you're stuck. You can go like this, but you can't complete the cycle. There's no edge this way. Yeah. Sorry? Yeah.
Could you also go about this thinking of strongly connected components? Like there's an SCC going from x1 containing x1 and x2, and x2 with rx1. And so like if you have an SCC where complementary literals are in the same thing, then I think the same thing is a cycle.
Okay. Yeah. We're focusing on cycles and what do strongly connected components represent in this graph, right? So I think that's exactly the next slide. Oh, well, let me warm. Yeah. So hold that thought on strongly connected components. So what I want to show, I think one direction is kind of easy to see. If there's a directed cycle, the formula can't be satisfied. But it would be very nice if this was a sufficient condition. It's necessary, but it would be nice if this was a sufficient condition to show the formula is satisfiable. Okay, so we know definitely if you find a directed cycle, it can't be satisfied. But does that mean if there's no cycle, it can be satisfied? That's not so clear. Okay, so that's what we're going to try to prove. So let me just set up and we'll come to the connected components on the next slide. So yeah, so that's what we just want to prove, that it's satisfiable if and only if, two kind of complementary literals don't appear in a cycle together. The easy direction, I think we've kind of gone and on about. So that's okay. And in the harder direction, okay, so suppose you look at the graph and you never have xi and xi bar in the same strongly connected component, or they're not in a cycle with each other. Then, if I can actually, in that circumstance, pull out a satisfying assignment, that would be a constructive proof. And that would also be an algorithm, right? So that's what we're gonna try to do. So, all right. So here's exactly the point that you were pointing out. So let's take like a strongly connected component of the implication graph. So I guess hopefully that's an accurate graph for some clauses, right? These are all in the same, it's a cycle, but strongly connected component. So what do I know about like all these literals? They have to be true? Is that true? What if they're all false?
They have some assignment that no true.
Yeah, so all we really know is that true can't go to false. That's the one real rule, right? So more so than necessarily them all being true, I think the real point is they all have to have the same assignment. You can't mix them anymore. Because if you mix them, then you eventually get some true false because it's a strongly connected component. Okay, so whenever you find a strongly connected component, you know that all the literals have to get the same assignment. So maybe all of these have to be true. That means when x2 bar is true, you're actually setting x2 to false, of course, and you have to read off the negation. Okay, so we know that in a strongly connected component, all the literals must have the same assignment. Okay. Oh, that one's supposed to do that much. Let's see if I can do better. Okay. I don't know. Okay, so another interesting observation about our graph is that there's this kind of complementarity going on. If we go back to originally how we construct these clauses, it's always kind of symmetric, right? So whenever you have an edge from A to B, where A is some literal, xi or xi bar, and B is some literal, you also have not B to not A. You have like that opposite arc going in the opposite direction. Okay, so every arc has some kind of like evil twin, twin arc in the graph. Okay, so right, and if we're trying to translate kind of from our two-set terminology to our graph terminology, right? In our graph, a literal x can reach a literal y if and only if, well, something in terms of reachability. Yeah.
Not y can reach not x.
Not y can reach not x. Okay, so if x can reach y, there's some path going from x to blah, 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 blah. Then that complementary tells you that like the not versions have the same opposite direction. Not y goes to not blah, not blah, not blah, not blah, back to not x. Okay, so because you always have this kind of opposite arc thing going on, you can make a statement like this. Okay, so I guess here I drew the strongly connected component from before, and then sort of the opposite strongly connected component was the opposite arcs. And then you'll see that every literal is replaced with its negation, and that the arcs are going in the opposite direction, although they're annotated by the same clauses kind of on each leg of this triangle. Okay, and if you extrapolate that sort of to a strongly connected component level, every strongly connected component has sort of this dual twin strongly connected component where everything's negated and reversed. Okay, so our graph has some kind of interesting symmetries going on. It's not your typical graph. All right, so good. All right, so now our goal is to somehow leverage these observations and actually try to put together an algorithm. Before I proceed and give away more answers, does anyone want to take a whack at really trying to leverage this graph to build an algorithm? I guess like every slide you get another chance with more hints to guess the rest of the algorithm, but yeah.
Maybe since trues can't they can't feed into false, we take like the topological equilibrium ball strong and complement it. The one that's the same, we just set that to be all true, and then work our way back to the
Okay, I think, I don't know if everyone heard, but it was something about topological sort the components. And you're worried about true to false, right? Which means that, maybe it's safe to start labeling sinks because they can't reach other components. So let me first go a little bit more slowly. First, if some component is a sink component, then it's kind of evil twin, the thing where everything is negated and opposite, it's going to be a source component. But why? Yeah.
all the edges have to be reversed.
All the edges are kind of reversed, right? So if I'm here and I have no in degree, then my twin brother has no out degree. Okay, just from this weird kind of reversing dual nature of this graph. Okay, so that's just one point. And now, okay, that also means that Okay, good. So now, if I don't know if you remember what was suggested, but the idea was to try to, maybe say work sync first. And we're really trying to avoid going from true to false, right? If we can figure out how to assign things in the graph so that we never go from true to false. You can go from false to true, and that's fine. You just can't go from true to false. And I'm looking at, a source component C, and its kind of twin sorry, I'm looking at a sync component C, and its twin is now a source component because it is dual nature. So this is at the front, this is at the back. They're going to get opposite assignments, right? Because if I assign this to be true or false, this has to be assigned false or true because they're all opposite variables. Okay, so what might I assign to the source and what might I assign to the sink? What would be most conservative? Yeah.
You want to assign true to the sink because false can point to true. Right?
Yeah, so if I assigned true to the sink, I don't risk any true to false because it's a sink. There's no one downstream. And also, if I assign false to the top, I don't risk anything up ahead, because that's also the receiving end of a true to false, right? So the conservative thing is to take your topological order, and the top gets assigned false, and the bottom gets assigned true, because you're trying to avoid true to false. So let's just try to go from false to true. Yeah. And that's it. I think that's the whole algorithm. So we just kind of gradually break apart, understand the structure of this. Obviously, this is a very clever algorithm, but we understand the structure of this graph, and then once we kind of get a hang of it, it's clear that there's sort of like a most conservative, obvious choice of what to do as you pull this thing apart. Yeah, it took a while. I mean, I think getting the setup is highly non-trivial, but then once we get to this point, it's quite natural to assign true to the sinks and false to the sources, and gradually just rip the graph apart. Yeah, and that's it. You'll be done. Yeah.
Why can't you do true to false, but you can do false to true?
Yeah. How come you can do or how come you can't do true to false and you can do false to true? So I think here we should just go back to how we set things up. So yeah. I mean, isn't it kind of weird that it's asymmetric? Like usually things come out symmetric. So how did this happen? It seems to have sort of fallen out from what was originally the motivation from the very beginning was, if I have this clause A or B, there's some forcing between them. Because now if I set A to be false, I have to take B. And if I set B to be false, then I have to take A. And these graphs are just encoding those two implications. And if you set this to be true, then that has to be true. If you set that to be true, then that has to be true. But if we just kind of parse, I guess, so what happened to the other direction? I guess it's just because we never said anything like, if you set A to be true, then B has to be false or something, right? Just A or B itself was always a little bit asymmetric. It's not doing all 4 2 to the 2 combinations or whatever. It's only just saying that if you don't take A, you have to take B. If you don't take B, you have to take A. And that's not covering all cases, only covering half the cases. And I think that's what eventually leads to the asymmetry in our graph. Yeah. So to review, I think that's also encapsulated in this part. In terms of understanding our graph, like if I plugged in my true false values into the vertices, but I hid all the labels on the edges, so I didn't know where it was coming from. If I looked at this graph and just made sure that I never have true going to false, I would know that these variables satisfy the original formula, the way it's set up. Right? So it just naturally slanted. Yeah.
So does this also imply that all the SCCs have different sets of literals, or can we have shared literals across strongly connected components?
Can you have a shared literal across, so the xi appears as xi in 2 different strongly connected components? Okay, so the question I'll open up to the class, can a literal such as xi appear in 2 distinct strongly connected components? Why or why not? Okay, I see a lot of head shaking, so why not? Yeah.
We defined the vertex to be xi, so whenever we added arrows to xi, we would always put it on the same one so they get.
So xi only appears on one vertex. And in strongly connected components, the way we defined it will partition the vertices, right? So strongly connected components are always disjoint. Yeah. Okay, so that's a very clever algorithm. Let's see. Okay, I guess here would be pseudocode, but it's not super interesting. Yeah, okay, so if you're given a formula, you compute the strongly connected components, check to see if any component has the same xi and xi bar. If not, then we'll just proceed to peel things like we did. You just topologically order the graph, remove a sink, remove a sort, its matching source, label them, and keep going. Okay. And then as far as, because this says come up in some questions, if you're doing a homework problem, this level of resolution I think is completely fine. You take the strongly connected components of the graph just as a sentence. You don't have to rewrite that algorithm. And then you can treat the strongly connected components like, oh, with this strongly connected component, I'll do this. Maybe on the homework, you work with the quote unquote contracted graph or something, where you shrink all the strongly connected components. You don't necessarily need to explain how to relabel all the vertices or anything. You can just work on that graph. We understand that's sort of straightforward. Yeah, because I think this is like, as it's more clear when you're teaching, but my goal is to just make sure it's as clear as possible what the real ideas are going on, but enough precision so that you know that the algorithm isn't like cheating, right? And I think this probably hits that mark. I think it's clear to understand what's going on and it's not cheating. There's a little bit of vagueness on a case-by-case issue, but that's the idea. Okay, what is the running time of our algorithm? Just to close this chapter, so I'll say that there's m clauses and n variables, right? Your input is expressed in terms of these two sat properties, right? Your input is in two sat. So how long would our algorithm take and why? Could go line by line. How long would the first step take? Yeah, like m or m plus n. I'm just going to scan things and build up the graph. You can do however way you want to. It's not so interesting. How long does computing strongly connected components take? M plus n. How long would it take to check if any strongly connected component has the same literals? Yeah, basically, I mean, maybe it's a little ambiguous about how the strongly connected components are represented, but I can imagine any reasonable implementation will, at some level, say, oh, this vertex corresponds to that component, it has some label, and then I just scan through, does xi and xi bar have the same label? Okay, and then when I process all the strongly connected components in some topological order, or reverse topological order, because I'm doing sync first, so probably in the worst case, like the biggest possible graph is when you have no strongly connected components. You just have the original graph and it was already a DAG or something. And now we're just kind of ripping something off and deleting its edges, ripping something off, deleting all the edges, right? So that would just take m plus n. And then, yeah, you return whatever assignment. So it's going to take m plus n overall. You're basically just computing strongly connected components and then just ripping out the components sync first order. No big deal. So it's quite fast, in fact. So not only is it easy, but it's about as easy as you can expect. We can do it in a linear time, faster than sorting. Which is kind of impressive. Okay, any questions? Okay, so that covers 2SAT. And 2SAT turns out to have a polynomial time algorithm. So maybe I can revisit, I can revisit the vote. And now that this turned out to be easy, see if anybody wants to change their mind. Okay, so we'll do the same procedure as before. This is round 2. Is anyone not going to vote? So we get to re-vote on max 2SAT. I'll put the line like this. Everyone's going to vote? I don't believe you, but that's okay. All right, who thinks that we can get an algorithm, maybe extending what we just did? Oh, the number might have gone down. Okay, and then who thinks it'll turn out to be hard? Okay, wow. First of all, great participation. Okay, so more people found it more likely to be hard after coming up with an algorithm for the most related problem in the world. Why? Yeah,
It's a Monty Hall problem. You only let it switch if it was hard.
money hall. So basically, because I'm mischievous. Okay, yeah. So, yeah, okay. And why would we be doing this now if they were both easy? Okay. So indeed, we are going to show it's hard. So your, you know, student instincts are correct. That won't always work in the real world, though. Okay, so we're going to try to show it's hard. Okay, and what's kind of amazing though is how they're so closely related, and the outcome is going to have such a different characteristic. That's really the point of the lecture. So, okay, now so I'm going to try to show that we're going to try to show that max2sat is hard, but it's going to be a little bit easier because the construction is quite subtle if we went via a very closely related problem, max less than equal 2sat, which is just saying that instead of having exactly 2 per clause, it's 1 or 2. And we're going to use this as an intermediary point. I mean, it's going to make more sense in hindsight why it's convenient for the technical calculations. But we'll figure out how to get from a very hard problem to max less than equal 2sat, and then from max less than equal 2sat to max 2sat. And that we'll be chaining kind of two things together. Okay, but this is largely for technical convenience. Okay. All right, so, okay, good. So we want to show that max less than equal 2sat, this slight variation of max 2sat, is at least as hard as solving Boolean sat, which is the same as 3sat and all these other sats. Okay, so the high level approach, right, like all these things, is, okay, so how do you set the proof? You know, we might start off with like a 3sat instance, right? We could have started with Boolean sat, but we already know 3sat can solve Boolean sat. So if I can show that I can solve 3sat, that's good enough, right? You can always chain these quote unquote reductions together. And somehow, some way, we want to convert that into this at most 2sat instance, okay? And show that if I feed it to a max 2sat box, right, I can somehow, and this is also interesting to point out, this is going to return some number, not a yes, no, right? Because it's going to tell you how many can be satisfied. And somehow I want to convert, okay. So it's going to somehow tell me the maximum number of satisfied clauses in that thing we make, and we'll need to also convert that number into a yes or no. Okay, so that's one slight plot twist, is that before we were going from like yes or no to yes or no. Here we're going from yes or no to a maximum number. We'll have to translate back and interpret it with respect to the original problem. Okay. All right, good. All right, so especially when you start from 3sat, it makes the challenge more clear. I'm just trying to get from 3 variables down to 2 or 1. Yeah, I give you a formula, every clause has 3 variables. We just want to get it down to 2 or 1. Any ideas? This one's like, the final eventual answer is super tricky, but it's still fun too. Like for example, we can take a single clause like A or B or C. Maybe A is actually not xi or something, but that's besides the point. You know, can I turn this clause into another clause that's 2 variables, or maybe a family of clauses that's at most 2 variables? Somehow this needs to become 2 variables. But you can introduce more clauses, you can introduce more variables, as long as we stay within roughly the same size. We can't blow things up exponentially. Yeah.
This problem at work where you have basically for each variable you split it into two, and you have A or Z and A or Z.
Okay. So this one here, each one of these is going to get split up. So you said A or Z and A or Z naught,
Yeah, and we just did the same thing for, I mean, of course, different Z, but
B or Z2, C or Z3. As usual, my handwriting is terrible. Something like this. Okay, we can at least acknowledge that we're turning into clauses of two variables, so that's a good start. But this is roughly telling me that A has to be true because these can't both be satisfied. B has to be true because they can't both be satisfied or something. So at some level, like, okay, so I think what this will do is like, it'll sort of count up how many of these are true, right? Because if you can make A true and B true and C true, then you can get all of these correct. If you can only get two of these variables, maybe A and B are true and C is false, then you'll be able to get these 2 points, but only one of these, depending on which one Z helps you on, or something like this. So from what I could tell, this gadget will kind of reflect how many of these individually are true. But our point system is a little different, right? Because our point system is if any of these are true, you only get 1 point. If two of them are true, A and B are both true, you still only get 1 point. So I think that this is really counting how many are true up here, and it's not quite capturing this or-ness about it. Or, yeah, disjunction aspect. But it's quite reasonable suggestion. Any other takers? Yeah, this one's like super hard to guess. Okay, so I'll just okay. Okay, so we're going to introduce one new variable y. Okay. And then we're going to make a bunch of clauses. So we're going to make 10 clauses. Okay, I'll go through them slowly. You're going to make singleton clauses for A, B, and C. And we're going to make clauses somehow not A or not B, not B or not C, not C or not A. I don't feel like me reading them off is any more comforting, but anyway. And then we're going to make the clauses Y, A or not Y, B or not Y, and C or not Y. So this is obviously not guessable, but hopefully at least thinking about it makes you appreciate it more. Okay, so what's the motivation? So what we're going to do here, okay, is I've roughly divided those 10 clauses in sort of their three roughly equivalent styles. Like we have the singletons here, and then all those like unions of knots in the second row. And in the fourth row, I have everything involving Y. And when you're doing max 2-sat, no matter what you set A, B, or C to be, you're going to choose Y to be whichever one helps you the most. Okay? And what we're going to do is we're going to look at, these are basically all the possible assignments up to kind of some symmetry. I could have set like all three to be false, A, B, and C to all be false, right? That should mean I don't satisfy it. I could set one of them to be true. I can set two of them to be true, and I can set all three of them to be true, right? And of course, you can vary which two you set to be true or something, but you'll still get the same score because everything is symmetric. So what we're going to do then is we're just going to tally things like, if I set all to be false, how many of the first row would I satisfy? How many of the second row I would satisfy? Third row, and then add them all up. And then something's going to emerge in this bottom row. Okay. So does that make sense what the table is trying to? All right, so let's start with the first column. So this is when all three are false. How many points would you get from the first row? 0. How about the second? 3. What about the third row? 3. Yeah, is that true? So you get You wouldn't, yeah, A would be false. So you're better off sending Y to be false here and getting these 3 points, and you throw away the singleton. So you get 3. Altogether, you get 6. Okay. All right, how about true, false, false? How many would you get from the first row? 1. How many from the second row? 2. Wait, I wrote 3. Do you get 2 or 3? If it's 2, then we're gonna have some major issues. 3, okay. So I think, yeah, because you need both of them to be true to not get the point, but always at least one of them will be false. And then what about the last row? Maybe this is trickier. How many points can you get in the last row? Three? Okay, so the one that's, yeah, I guess you would just set Y to be false, right? So maybe you get 1 point for this one, and then you have you can either choose this or these two. You just choose those two. You get 3. Okay, everything will add up to 7 this time. That's good. There's some difference between. All right, let's look at the third column. So true, true, false. How many points would you get from the first row? How many points would you get from the second row? 2. I think that false will get you 2 of the clauses. All right, how about the third row? What is it? That's okay. 3? Did everyone get 3? Okay. So add up to 7. Okay. Now let's do the last column. How many would you get from the first? This is true, true, true. How many would you get from the first row? And in the second row? 2? People got 2? What? Are you just like saying numbers? It's like Anchorman. Like whatever you guys say, I just go along with. I have no idea. It's like a prompter. Okay. And then how many would you get in the last row? 4. Okay. So you get 7. All right. So what is the significance of the last row? 6, 7, 7, 7, 7. Or 6, 7, 7. Yeah. Okay. Whatever. Clearly, there's 1, 6, 3, 7s. But why does that matter?
The 6 is only there, but all of them are off.
Ah, okay. This is the one assignment that wouldn't satisfy our 3 stat clause. Right? So once you can't satisfy, you'll get 6 points. All of these would satisfy the clause. It has at least one true. Each of them would get 7 points. Right? So this crazy gadget, which obviously is quite hard to come up with, is complicated enough to explain in hindsight, right? Is somehow able to only use at most 2 variables per clause and distinguish between satisfying and not satisfying the original 3 clause. Okay. So if I have a gadget like this, what would my whole construction be? So I give you a formula. Every clause has exactly 3 variables. I have this trick. How would I put it all together? Yeah.
You would do the transformation and then run max 2sat, and then if that's less than 7 times the first clauses, then it didn't satisfy.
Perfect. So we're going to apply that to every single, it's probably too hard to read this. We'll apply that to every single clause, right? And if our formula is satisfiable, if there's some way to satisfy my original 3 sat clause, then I should be able to plug that into my 7 times bigger, or no, 10 times bigger formula, right? Because every clause got turned into 10 smaller ones. And I should be able to get 7 M points by choosing the right Ys for each of those gadgets. right? So if my original formula was satisfiable, I should be able to get 7m. And then conversely, yeah, okay, so maybe, yeah, so you're doing something like this. Okay, let's see, I thought I had this. Okay, so you make 10 clauses for each one, and whatever, you create a big satisfiable. Okay, so if f is satisfiable, right, then you can extend, okay, then we know you can choose y1 to ym so if x1, I'm just kind of going slowly to set a moderate example. If x1 to xn satisfies f, right, then our lemma says, okay, so x1 to xn will satisfy every one of those three clauses. So that lemma we just kind of work through says that I should be able to choose the y for each of those clauses. So I get 7 points for each one, right? So there exists some way to choose y1 through ym, that's one per clause because there's m clauses, such that altogether x1 through xn, y1 through ym, satisfies 7m clauses of our two-sat formula G. Okay, so if I start with F, I'll call that two-sat formula we make G. Okay, so that's one direction. I think that's the easier direction. Now, I want to do an if and only if, right? So I think the algorithm we all have in mind is I start with F, I make this two-sat formula G, that's 10 times bigger, 10 times as many clauses. I get the max two-sat and see if it's at least 7m. If it's at least 7m, I'll say yes. If it's less than 7m, I'll say no. Okay? Now, you really want to make sure that yes means yes and no means no. Okay? So, what this direction here says is, okay, so if f is satisfiable, then g will be at least 7m satisfiable. That means, actually, if you go through it slowly, that no on the g side means no on the f side. It's a contrapositive of if f is yes, then you get 7m down here. But if I'm thinking of like, does no mean no in terms of does no from the bottom right mean no to the top left? That's sort of it's a little confusing, but if you go through it slowly, it is the logical thing. Only under time pressure or like if you don't sleep, then you might mix it up. We all mix it up. It happens a lot. But this really shows that no for the two-sat is it bigger than 7m implies no for whether f is satisfiable. Yeah, it's a little confusing, so you just want to take, at least I take it very slowly because I always mix this up. Okay, so now how could I try? Now I just want to show that yes, I can satisfy 7m clauses implies yes, f is satisfiable. Right? So how can I try to set that up? So I could write something like, well, if f is not satisfiable is maybe another way to do it, right? That's sort of the contrapositive. If I can show that if f is not satisfiable, then you can't satisfy 7m and g. That would be, again, it's super confusing, the contrapositive of yes implying yes. Okay, so anyway, the opposite direction that we haven't shown is that if f is not satisfiable, then you can't satisfy 7m and g. Yeah.
If f is not satisfiable, then at least one of the clauses, once expanded, we only return a 6 score.
Yeah.
And so your score will fall short of 7m.
So I think there's two things to point out. Okay. So I think one thing to point out is the lemma implies you get at most 7 points per clause. Okay, because you want to be able to rule out situations where like you get 6 points here, which means you didn't satisfy that clause originally, basically, but you got 8 points somewhere else to make up for it. So it is important that it's capped at 7. Okay, and then yeah, the second point is, so x1, xn, does not satisfy f, right? Because f is not satisfiable. That implies there's some clause C. Maybe I'll write CI, that's not satisfied, x1 to xn, which implies, I mean, I'm kind of writing shorthand, you know, in that the CI's gadget you satisfy at most 6 clauses, no matter how you choose that yi variable. Okay, so if you just want to tease it apart slowly, and I feel like my handwriting is terrible, but you know, all you know about f is it's not satisfiable. So if you gave me any x's, right, I know it doesn't satisfy f, so I can find at least one clause that it messes up on. And then if I look at that clause and I go back to our lemma, no matter how I choose that extra y variable for that clause, I can only get 6 points. Okay, so it's just teasing apart slowly what I think we all agree on. If it's not satisfiable, then there must be something wrong. That something wrong is go pinpoint that clause that's not satisfied. Some clause is not satisfied. That clause you get less than 7. All the other clauses you get at most 7. So you can't do better than 7m, or you can't get 7m. That makes sense? So you have m different things. You can get at most 7 points, but at least one of them you're only going to get 6. So you can't get 7m. It has to be strictly less. It could be much less if there's many clauses you're getting wrong, but yeah.
So just to reiterate, the way you're proving, we can imply f's state from like the return value is by looking at the return value and give it what f would be, and then looking at those contrapositives for both cases.
Yeah, so in this case, we are kind of doing the contrapositives of no means no and yes means yes, which is really what you want to show. I mean, you want to show that kind of your reduction is sound and complete, so to speak, right? But basically, you want to make sure your answer you're interpreting correctly with respect to the original problem. So that means you do need to do both directions somehow. And I guess the way I set it up was sort of the contrapositive of those statements, where I showed if f is satisfiable, then you can get 7m. And if f is not satisfiable, then you cannot get 7m. And if you kind of work through that slowly, the first one, f is satisfiable, means you can get 7m. That implies that a no down here must mean a no for the original problem. And in the second one, if f is not satisfiable, then you can't get 7m. If you work through slowly what that implies, it means that a yes down here must have been a yes up here, otherwise you'd have a contradiction. Yeah, so it's a little confusing, especially when I say it out loud. It looks like everything is getting flipped around, but if you just take your time, you do it on paper, it's usually okay. So I mostly encourage you just take your time, because mostly everyone messes it up, but when you mess it up, it's like, they were in a rush. Okay. But it is important to understand the need for both directions. And it's quite common, especially when we're just starting and getting practice, to accidentally prove the same direction twice. Because things are kind of getting flipped, but you didn't quite flip it enough or something, and you end up proving the same direction twice. That makes sense. That's quite common. So just go slowly and tease it through. If you have the right algorithm and reduction, you probably have worked through both sides somewhat intuitively in your head. So as usual, the exercise is, okay, how do I get this awkward mumbo jumbo down on paper in a clear, verifiable fashion? You know, it's as much about articulating as actually solving these things. Okay. Is that okay? Okay, good. I think we'll finish early. So, okay, no, we have a little more. We will finish on time, but we won't necessarily finish early. Okay, so all we've shown now is that this problem at most 2-sat is just as hard as 3-sat, which is just as hard as Boolean sat. But we were originally interested in exactly 2-sat. So is there something special about exact 2-sat where 2 variables somehow makes it easier? We haven't ruled that out yet, although maybe it'll be less surprising at this point. So, right, so yeah, so our goal is to kind of, yeah, so for example, we've sort of done, why, this picture is wrong. That's okay. So we've sort of done, forget it. Okay, so we've done this top left corner here, although that label's misleading. And we've gone into max 2-sat. And what we want to do is we want to fill in this quadrant down here, right? If I can go from max 2-sat, or at most 2-sat, and show that max 2-sat solves this problem that we just used, then that would imply it can solve the original problem. Okay, so, right. That's sort of our situation. We're going to fill in this bottom right. Okay, but this one is not as devilishly tricky. So I give you a formula with at most 2 variables per clause, right? And you're trying to get it to exactly 2 variables per clause. And so the only issue is these singleton clauses. Just A appears or something, right? In a max situation. So how can I take my singleton clauses and turn them into 2 variable clauses? We've actually already done it once in this class. Sorry, say that again? A and not A? Oh, A, okay. So I'll just make a new variable Y, and then this already came up before. I'll do A or Y and A or not Y, right? And then, Y can be whatever you want. So for example, if A was true, then how many, oh, no matter is not quite true. So if A is true, then how many of these can you satisfy? So I took A as true, and now I've created 2 of these clauses. So you can either satisfy none, 1, or 2. But what's the best you can do by choosing Y appropriately? 1? Okay. You get at least.
One of them is true.
Oh, okay. So I think actually no matter was just fine. I confused myself. Okay, 2. No matter what you do for Y, they're both satisfied. Okay. Now, if A was false, so you're not satisfying the singleton, how many of the 2 can you get? 1. Okay, good. So now, when you should be getting 1 point, you get 2 points. When you should be getting no points, you get 1 point, and it's consistent, right? So we have this nice clean separation. Okay, so if I put everything together, I'm just going to replace every singleton clause with 2 of these double clauses. And now how do I kind of map things? So I start with some F, it has at most 2 variables per clause. I turn it into some G that has exactly 2 variables per clause by introducing this little buddy trick. And now I get the maximum number of clauses I can satisfy in this one with exactly 2 variables. And I want to map that back to how many I can satisfy with 1 or 2 variables in the original formula. So what's the math? Yeah.
Subtract the number of singleton clauses.
You subtract the number of singleton clauses because each of those gets a free point now. Is that written? Hopefully that's written. Okay. So, yeah. So that's right. Okay. So if K was that number, then you would add K. Well, no, you subtract K from what you got for G. Right. Okay. So, good. All right. So that's it. That's much easier than the first leg of our proof. We're just adding these auxiliary variables to pad the 1 variables into 2 variables. And you kind of gives a free point, no matter the value of A. So if you put everything together, okay, this picture is right? This was the first one that we did, the really clever table. The second one, a little bit easier. And overall, now we've completely shown that max 2-sat is just as hard as 3-sat, right? I can start with a 3-sat formula. I convert it to something with at most 2 variables per clause. And I can take that and convert that into exactly 2 variables per clause. So if I can fill in this box down here, then I can fill in this box in the middle, and I can solve ultimately a problem that we already felt might have been hard coming into class. Yeah, question.
Why can't we play this game the other way and turn 3-sat into 2-sat? We solve 2-sat, right? So why doesn't the implication of the fact?
Oh, sure. So one can also ask, can I use 3-sat to solve max 2-sat?
No, I was thinking like we solved 2-sat earlier. We put on the time, right? So
Oh,
and we know we can transform 2-sat problem into a 3-sat problem.
Yeah.
or
Okay.
mathematics.
So let's focus on this one because that's almost the whole point of this lecture. At some level, I presented two problems that are almost identical. 2SAT, max 2SAT, right? With dramatically different outcomes. 2SAT, we got a linear time algorithm as fast as you can possibly imagine. And it was basically just like SCCs at the end. Max 2SAT, we didn't even come close to an algorithm. We were able to, in fact, embed any Boolean SAT inside max 2SAT. So what happened? Actually, there's no right or wrong answer here, but why, unless we're, I mean, how come we can't use 2SAT to solve Boolean formulas? Or like, what happened? Where was the gap? Like, anyone have any reflections?
Set is only like if that can be satisfied, max two set is like how many can be satisfied with.
Well, certainly that's the definition of the problems, right? 2SAT, you have to satisfy everything. Max 2SAT satisfies as much as possible. I don't know if that brings much comfort. It's still, yeah.
Maybe like 2SAT can't be generalized to the rest of them because it's a subset that has this specific property.
Well, it's definitely a subset, so it doesn't automatically generalize. But what happened? I don't know. It still feels like it's just open to interpretation. Yeah.
For 2SAT, we might know that because the booleans are base 2, then we can, from one element, we can know the other. And so that's something that we know about the problem that we don't necessarily have for 3SAT.
Yeah, I mean, both problems are Boolean based too or whatever, but with 2SAT, somehow that extra constraint, they all have to be satisfied. They let us go down this path of like A forcing B, or not A forcing B or whatever, right? And with max 2SAT, even if there's only two variables per clause, there's like a third choice of whether or not to satisfy the clause at all. Right? It feels like there's like half a degree of freedom sitting in this max, which doesn't seem like much, but somehow eliminated this A has to imply B immediate logic. So some gap opened up there. And at least immediately, that's why we can't do the exact same thing, is I can't argue so strongly that if I set this to be true, that has to be true. Because I could also just forfeit that clause, right? So I still can have two choices, which is sort of like 3SAT, right? Even if I know one variable, I still have two remaining choices. I can't eliminate things as clearly. But at some level, this is sort of the unsettled state of affairs in a lot of computer science, right? There's a lot of problems. Some can be solved, some cannot be solved, and they may look a lot like each other. Okay? In fact, we don't have a great answer, as we'll kind of keep finding out for the next couple of weeks, why some can't be solved and others can. The best explanation I can give you for at least this case is that I've proven to you that I can solve 2SAT, and well, you guys practically proved yourself, but we've proven that max 2SAT can solve Boolean SAT, and I feel more willing to admit that Boolean SAT is very hard, right? So insofar as we have this proof, I'm willing to say, okay, maybe max 2SAT is harder because I think Boolean SAT is definitely different from 2SAT. I can see a big difference between Boolean SAT and 2SAT, even if I don't see a big difference between 2SAT and max 2SAT. Okay, so we can still kind of rigorously tease apart and understand this landscape, but at some level, we're in this state of dissonance as well. But okay, I'll see you Tuesday. Enjoy reviewing.